Hi, welcome. This is going to be the third, possibly the final lecture on partial order. Today, what we are going to do in the second lecture, we applied Zorn's lemma to prove the existence of a maximal ideal in a commutative ring with identity. Today, we are going to do two applications. Both are in linear algebra. The first one is the existence of a basis for any vector space over any field. And so vector space may be finite or infinite dimensional. And the second application, though it's linear algebra, it's some kind of a preliminary to Hahn-Banach theorem. Okay. So essentially the algebraic aspect of Hahn-Banach theorem is what we are going as a second application. All right. Okay, let us get started. Yeah. Theorem. Let V be a vector space over a field F. As usual, I will take F to be R. Okay. And let A a non-empty subset, or it could even be empty, a subset of V, so that A is linearly independent. Okay. Now, you do notice that V is any vector space over R, and I wanted, so it's there is a possibility V is infinite dimensional. So you, and therefore a subset of V could also be an infinite set, possibly. Okay. So what do I mean by saying A is linearly independent? So one has to remember the definition. Okay, we say A is linearly independent. Okay, any subset A of a vector space V is linearly independent if and only if, okay, every finite subset, okay, let us call it a E of A is linearly independent. Okay, every finite subset. Okay, this definition you may think it's somewhat a little weird, but if you go back or watch my video on linear dependence independence, you will see it is the most natural definition. It is the only definition which works. Okay, which is needed. In fact, the usual thing like summation ci va equal to 0 implies all ci is 0, etc., etc. They are all the corollaries of this definition. Okay, so let me repeat. A is a subset of V, possibly infinite set. When do I say it's linearly independent? For every finite subset E of A, then E is linearly independent. Is that okay? Right. So if it's not linearly independent, that is, it's a linearly dependent, what does it mean? There exists a finite subset E of A, so that E is linearly dependent. Okay. Please pause, review this definition. If this is the first time you are going through this. Okay. So what we want to prove is the following theorem. V is a vector space over a field, possibly we will take it as R. Let A be linearly independent set. Okay, then there exists a basis B of V such that A is a subset of B. Okay, so whatever linearly independent set you give me, I can extend it to a basis of the set. In particular, okay, we will assume V is not equal to 0 to avoid triviality. Okay, is the statement clear? Okay, now we want to prove that. Okay, proof is easy. Now, what is the definition of a basis? So in a general vector space, I say a subset B is a basis. Okay, there are equivalent definitions. Again, I had given in one of my videos. If B is maximal linearly independent. Okay, one, or equivalent condition is B is linearly independent and a spanning set. And there is also a third condition. Let's not worry about. Okay, please again watch my video about a basis of vector space, equivalent conditions or equivalent definitions of a basis. So when I want to prove there exists a basis B of B, what I plan to do is I will try to produce a set B which is maximal linearly independent. Okay, therefore we have to find B which also contains A, and B is maximal linearly independent set. Okay. Now again, let us recall, what do I mean by maximal linearly independent? If you tell me B dash is linearly independent and B is contained in B dash, then B equal to B dash. Okay. B is maximal linearly independent if B dash is any linearly independent set so that B is contained in B dash, then B dash must necessarily be equal to B. Okay. So you notice that we already recalled three definitions. First is what is meant by linear independent set in any vector space, and what is meant by a basis, or first, what is meant by a maximal linearly independent set. Third, what is meant by a basis. Okay. Please understand these things so that you will be able to follow the rest of the talk. Okay. Now what do I do? So again, I want to use Zorn's lemma. So when I want to use Zorn's lemma, as I said, the most important case is subsets of a given set. Okay. And there, what is the partial order? Contain inclusion relation or containment relation. That is our thing. So, but what do I want? I want a maximal linear independent set. Is that all right? And I also need my B to contain A. Therefore, what kind of a collection of subsets? So I want to construct script A, which is a collection of subsets of P of B. Power set, that is subsets of B. So what kind of subset should be there? Okay, that's what you have to ask. So first thing is, okay, you should contain, if a B has to be here, then B must contain A. That's the first condition. And second condition is I am looking for a B which is maximal linearly independent. Therefore, this B should also be linearly independent. You understand that? So I'm trying to motivate how do I define script A. Script A is a collection B, a subset of B, so that first B is linearly independent and second B contains A. So what's the first question you should ask? Whether this collection is non-empty. That's very clear because my set A is already here. I take B equal to A, then A is linearly independent and A contains C. Therefore, this is not empty. Okay. Next is what is the partial order? That we already know. So you give me B1 and B2 here. I say B1 is less than or equal to B2 if and only if B1 is contained in B2. Okay. Very good. So this we had already checked. This is the partial order, etc. This is very easy. This is a partial order. Therefore, this script A with this is a partial ordered set. Right? I want to apply Zorn's lemma. To apply Zorn's lemma, what is that I have to make sure? I have to make sure it satisfies one important condition. What is the condition? The condition is if you give me a chain, that is, suppose you give me a B, okay, this is a subset of A, so that B is a chain. That is a totally ordered subset. Okay, then I have to say whether there exists some B in script A said that B is an upper bound for any set in script A. Oh, is that clear? Yeah. If you want, let me call it as some. Okay, let it be all right. Okay. Yeah. Now this we had already seen in the earlier lecture. We have seen how to find an upper bound. If B is a totally ordered subset, you define B. Maybe I will call it something like call it a C. Therefore, that is C. Okay. B is less than or equal to C for every B in script B. Yeah. Given a total ordered set, I have to find a C which is in A, so that C is an upper bound for every element of B. That means B, give me any element B in B, B must be less than or equal to C. I have to find such a C. Right? So we had already know what is the trick. The trick is look at the union of all elements in script B. Right? I hope you all of you remember this is X in B, so that X, okay, there exists a B in script B, so that X belongs to B. Collection of all elements in this. Okay. So naturally, by very construction, C is a super subset of every B in script B. Therefore, for all B in B, we have B is less than or equal to C. This is all right. Therefore, but then that's not enough. What do you have to show? I have to show C belong to A. You understand that? When do I say this is, I want to apply Zorn's lemma to script A, the partially ordered set. That means give me any chain B, I have to find a C in script A. So that C is an upper bound of B. You follow that? So I have to check whether C belong to script A. So to C belong to script A, what is the first sec? A is contained in every B, right? For every B in script B. Therefore, A is contained in C. So the second condition is met. Now I have to check whether the first condition is met. That is, I have to check whether C is linearly independent. Yeah. But that's easy. When do I say C is linearly independent? Okay. You give me any finite set V1, V2, Vk in C. Then I have to say this finite set, this is linearly independent. This is what I have to prove. Right? Okay. Now how do I prove that? Don't think of C1 V1 plus C2 V2 plus Ck Vk equal to 0 implies all C1 C2 Ck is 0. You don't need that. There is a much smarter way. Now let us look at V1 belong to C. Therefore, what do I know? There exists a B1. Okay. Therefore, for each I, for I between 1 and k, there exists a Bi in the totally ordered subset B, the chain, so that my Vi belong to Bi. Yeah, because C is the union of all B. You understand? Right. Now, what do I know about this collection B1, B2, Bk? This is a subset of this, but and therefore this is a finite subset of a totally ordered set. So we had already seen in the first and second lecture, any finite subset of a totally ordered set has a maximum, right? Therefore, without loss of generality, assume Bk is the maximum of B1 to Bk. What does that mean? This means for all I, Bi is less than or equal to B, that is Bk. That is Bi is contained in Bk. But what does that mean? This means my V1, V2, Vk, they are all in Bk. And what do I know about Bk? I know Bk is linearly independent. What is the meaning of This set being linearly independent, any finite subset is linearly independent. That means V1, V2, Vk, this is linearly independent. So what I have shown, so I wanted to prove C is linearly independent. So you give me a finite subset V1, V2, Vk of C, then I have to prove it's linearly independent. Have I proved it? Yes. Therefore, I have proved A is contained in C and C is linearly independent, and for all B in script B, B is less than or equal to C. Therefore, C is an upper bound. Script B. Do you follow that? So I have the collection A, right? Okay. Now what I have proved, it's a partially ordered set and it satisfies the conditions for Zorn's lemma. That is, any chain has an upper bound in the partially ordered set. Therefore, Zorn's lemma tells me there exists a maximal element. Yeah. So by Zorn's lemma, there exists, let me call it a B naught in A, so that B naught is a maximal element of script A. You follow that? Notice that this is a maximal element for script A, right? What does that mean? So in particular, A is a subset of B naught. Yeah? Okay. And I know it's a maximal element of A, therefore B naught is also linearly independent because it's an element of script A. So B naught contains A, B naught is linearly independent, and B naught is a maximal element of A. Does that imply it's a basis for V? No. This is a subtlety you have to pay attention. This is a maximal element of A, but what I am supposed to show is B naught is maximal linearly independent subset of V. You understand? Right? So let us do that. This is very easy. The only thing is you should understand the need to prove this. Just because the word maximal occurs here, and you also know it's linearly independent, you cannot put them together. Okay, they mean something. This is a maximal element of script A, and as I said, it's linearly independent. But what I want to prove is B naught is a maximal linearly independent subset of V. Okay, so what does it mean? You give me a B dash linearly independent, okay, and said that B naught is contained in B dash, then I have to prove B dash is B naught. Then B naught will be maximal linearly independent. Okay, this is linearly independent subset of V. You follow that? Okay. Now, suppose B dash is linearly independent and B naught contains B dash. Notice that B dash belongs to script A then. Yeah, because A is already in B naught and therefore it's also in B dash. And B dash is linearly independent, therefore B dash belongs to A. Now B dash is an element of A and B naught is maximal element of script A, right? Therefore, what do I know? And also you have B naught is less than or equal to B dash. That's also given. And B naught is a maximal element. Therefore, this shows B naught equal to B dash. Do you follow that? Okay. Please pause, review, and proceed. The only thing you should understand is why I have to prove B naught is maximal linearly independent set. Many students will believe just because it's linearly maximal element of A and it's linearly independent, you cannot conclude it's maximal linearly independent subset of V. Okay, but that proof is easy. Okay, the second application, okay, of today. This is actually third application, but it's the second application of today. Okay, again, B is a vector space over a field. Again, we will take it for convenience R. We don't really need anywhere, okay, what field we are using. Anyway, okay, and suppose W is a vector subspace of V. And further assume F is a function from W to the ground field R, which is linear. You understand this? So what I want to know is whether I find an extension. That means whether there is a G B to R which is linear, and such that when I restrict G to W, it should be F. That means G of W must be equal to F of W for every W in script W. Whether such an this called G is called an extension of F to V. What kind of an extension? Since F was linear, I want F to G to be linear also. Do you understand this question? Okay, this is algebraic version of Hahn-Banach theorem. Okay, and pure linear algebra wise, this is utter triviality. I will give okay, I I will give that proof later. Because okay, this is purely from algebraic point of view, it's utter triviality. Yeah, I can make use of the first application, existence of basis, to prove that. But let's not worry about. Okay, so I want to proceed in a slightly different way. I want to complicate the easy proof. Okay, maybe I will give the easy proof first. Okay, what is the easy proof? Easy proof is, suppose B1 is a basis of W. Why does it exist? Maybe call it A. A is a basis of W. Okay, because every vector space has a basis. We just now saw that. How do I know every vector space has a basis? From this, how does it follow? Since V is non-zero, right, I can start with A to be any singleton V. V is non-zero vector. Then it's linearly independent. Therefore, there is a basis. Are you following me? See, I only proved there is a basis. And from this, from this, how do I conclude any vector space has a basis? So I have to start with A. Which A I will start with? Since V is non-zero, start with any non-zero vector V. Consider the singleton set V. Then that's a linearly independent set. Therefore, there is a basis B of V. So this theorem actually proves the existence of a basis. Okay. Now you can see how I go back and forth. Okay. Right. Anyway, come back. Therefore, what I know is there is a basis, call it A of W. Now, A is also a subset of V. It's a linearly independent. Therefore, by the last theorem, there is a B, a basis of B, so that A is also a subset of B. Right? Now, suppose call B as union of, let us say, Wi union Vj, where this is my A. Okay, these are the extra elements to find a basis, right? Are you following what I'm saying? So let A equal to some Wj, J running something, or some indexing set. Let's not worry about such things. So this is a basis of W. So extend it, Bx. Okay, there is a basis B of V, which contains A. Therefore, there are extra elements. Call them as maybe Vi, sorry, Vi, and call these extra elements as Vj. Okay, therefore none of the Vj's are in W. Right? Now, what do I do? Now you recall the theorem, any linear map from vector space V to W is uniquely determined, okay, by its action on a basis. Okay, right? So that I'm making use of that. So let me define G of Wi to be f of Wi for I in the script I, the indexing set, and G of Vj equal to 0 for every j in script j. Right? Then there is a unique linear map G from V to R, so that G of Wi is f of Wi, G of Vj is 0, and this G is extends f. Is that clear? Because any vector in V will be written as summation sum ai wi plus summation bj wj, but notice that these are all finite sums. Therefore, when I operate g on this, how did I extend g to this? By this action. This is summation ai g of wi plus bj bvj 0, g of vj which is 0. This is wi, but this is summation ai f of wi. You understand that? Therefore, if my g of v, therefore if my v was already in w, then v will be summation ai wi, and therefore what is g of v? G of v is f of v. That's what you proved. Okay. Pause, review, proceed. Okay. So this is utterly trivial proof, but I want to complicate the proof. Why do I want to complicate the proof? Because if you look at this way, you will understand this explains half of the Hahn-Banach theorem, the algebraic part of Hahn-Banach theorem in functional analysis. Okay. So let us look at. So what we have is V, I have W, vector subspace of V, and an F from W to R. I want to extend G from V to R so that G equal to F on W. Okay, this is what I want. Okay, so how do I plan to do that? Right, the way is very interesting. So what I look at is I look at the set of all subsets U G, where U is a vector subspace of V and such that W is contained in U. And what is G? G is a linear map from U to R. Notice that W is already a subset of U, therefore G I can restrict to W. This I want it to be F. Do you understand this? So unlike earlier thing, now my collection is going to be ordered pairs, where the first argument U is going to be a vector subspace of V containing W, and G is a linear map from U to R which extends F. You understood this? So I am looking at collection UG. Okay, so that this. Okay, this is my collection U. All of you understood that? So it is not only subsets, it's a ordered pair. The one is first is a vector subspace of V which contain W. Second thing is a function from U to R, linear map, of course linear, and such that it extends F. Do you follow that? Okay. Now suppose you are given U1 G1 and U2 G2. I want to say I want to introduce a partial order. What is a very natural partial order you can think of? With respect to the first coordinate, it's very easy. So I would say if and only if u1 is contained in u2, that is u1 is less than or equal to u2 with the inclusion partial order. Yeah. Now what will I do with the g1 and g2? Notice that. Remember, I want my final element g to be an extension, right, to all of v of extension of f. Therefore, what do I want is this g2 must be an extension of f, and g1 is also an extension of f. But then what I want is, since u1 is contained in g2, therefore g2 must be an extension of g1 and g1. You understand this? This is what you have to pay attention. Okay, u1 is less than or equal to u2 is very easy. Now g1 is less than or equal to g2. How do I make sure? Okay, notice that g2 restricted to u1 must be g1. Therefore, naturally g2 also extends f. Okay, have you understood? Now is it a partial order? So we want to check whether it's a partial order. Whether this is a partial order. First, why this is non-empty? That's because w f is already in script u. I can take u to be w and g to be f. Yeah, therefore it's non-empty. Why it's a partial order? First you give me ug, then it's less than or equal to ug. That's very clear. Yeah, good. Next is you tell me u1 g1 is less than or equal to u2 g2 and u2 g2 is less than or equal to u1 g1. Then I want to know whether u1 equal to u2 and g1 equal to g2. But that's obvious. Why? Notice that u1 is less than or equal to u1 g1 is less than or equal to u2 g2. This implies u1 is subset of u2, and this implies u2 is a subset of u1. Therefore, both imply u1 equal to u2. Right? Okay. Now, once u1 is equal to, then it follows g1 is g2. Why? Start with any x in u1 which is equal to u2. Then what is g1 of x? Remember, this says g1 restricted to u2 must be g2. Therefore, it's g2 of x. You understand? Or you can use the other way around also. Are you following? X is in u1 which is also in u2, right? Therefore, x is in u2 and u2 g2 is less than or equal to u1 g1, and g1 therefore is an extension of g2. That means g1 of x must be g2 of x because x is an element of u2. You follow that? Therefore, we have proved for every x in u1 is equal to u2, we have proved g1 equal to g2. That means this. Okay, please pay attention, follow. And similarly, the third, transitivity. So therefore, this proves symmetry. No, sorry, antisymmetry. Then transitivity. So again, let us look at u1 g1 less than or equal to u2 g2 less than or equal to u3 g3. So this is given, okay, and this is given. So I have to prove u1 g1 less than or equal to u3 g3. Yeah, but that's easy again because u1 g1 less than or equal to u2 g2. This implies u1 is contained in u2, and this implies u2 is contained in u3. Therefore, this implies u1 is contained in u3. You understood? Therefore, u1 contained in u3 is clear. Next, what do I have to prove? g3 restricted to u1 is equal to g1. Yeah? If I want to say u1 g1 is less than or equal to u3 g3, what should I do? Restrict g3 to u1, I should get g1. Right? Okay. Now let x belong to u1. Yeah? Now what do I know? Since x belongs to u1 and u1 g1 is less than or equal to u2 g2, therefore I know, okay, this is contained in u2, therefore g2 of x is G1 of X. Do you accept it? Because of this, right? Okay. Now, now X is in U2 and notice that U2 G2 is relating to U3 G3. Therefore, G3 of X is in U1 and hence in U2. And because of this relation, U2 G2 is relating to U3 G3. G3 of X must be equal to G2 of X. But G2 of X equal to G1 of X. Yeah. Therefore, we have shown U1 G1 is relating to U3 G3. Okay. So what I have shown, this collection of all such, I will call this a collection of extensions of F. This collection of extensions of F is non-empty, partially ordered set is okay with the partial order as defined. Next, I want to apply Zorn's lemma. To apply Zorn's lemma, I have to make sure something. What should I make sure? I have to show something. So let script A be a totally ordered subset, okay, of U. Okay, this is a chain. I want to know whether there exists. Okay, let us call U0, G0. Okay, in script U so that U0, G0 is an upper bound. Yeah. Okay. In particular, what should happen? For every U in script A, U must be less than or equal to U0. Right? If such an upper bound exists, this must happen. So how will I find U0? I'm sure all of you can now define. What is that? U0 is union of U. Okay. U such that U, G belong to script A. That is, take the union of all the first coordinates here. Okay. This is set of all X in V so that there exists UG in script A so that X belong to U. Remember, use a vector space. Vectors are space of V. Yeah. So by very construction, for every UG in script A, U is less than or equal to U is contained in U0. By very construction. Right? Now I want a G0. G0 should be what? It should be a function from U0 to R. So how do I define? Okay, there is only one obvious thing. Start with any X in U0. I have to define G of X0. Okay, I'll call it G0 of X0. So G0 of X, sorry. For X in U0, I have to define G0 of X. Right? Now X belongs to U0. What does it mean? That means there exists U, G in script A, the totally ordered subset chain, so that X belongs to U. Right? Therefore, I define G0 of X to be equal to that G of X. What is this G? This is the G so that UG belong to script A and X belong to U. Pay attention. Yeah. Now, is there a potential problem? Yes, there is a potential problem. Why? My X may be in some U1, G1 in script A also. And it may also be in U2, G2 in script A. When I say X belong to this, what I mean is X belong to U1, X belong to U2. Right? Then I would define G0 of X equal to G1 of X. I could also define it to be G2 of X. You understand? So I have to make sure that G0 is well defined. That is, G0 is well defined. I have to check it. Okay, that is very easy. Okay, why? Now let's look at U1, G1 and U2, G2. Where are they? They are in script A. What do I know about script A? It is a chain that is totally ordered. Therefore, one of them is less than or equal to the other. Yeah. Therefore, without loss of generality, let me assume u1 g1 is less than or equal to u2 g2. You understand? All right. That's where we are using totally ordered set. Now, since it's totally ordered, this now x belongs to u1, of course, also is in u2. But remember, u1 is g1 is less than or equal to u2 g2. Therefore, let us look at g2 of x. Now, x belongs to u1 and g2 is an extension of g1 and x belongs to u1. Therefore, g2 of x is same as g1 of x. You understand? Therefore, I have proved it is independent of which thing. So, whatever ug, and if x belongs to u, I can define g naught of x to be g of x. It's well defined. Are you following? Please pause, review, proceed. Okay. So, what I have shown? I defined the function g naught from u to r is well defined. It is a very natural way of defining. Okay. Very good. So, let us look at u naught, g naught. Okay. I want to say it's an upper bound. So, I know u naught is okay for every u g in script a, u is contained in u naught, and also for every u g I also know u g is less than or equal to u naught g naught, right? You understand that? Yeah. Do you follow this? Because if x belongs to u, then I have to say g naught of x equal to g of x. But that's how we define g naught of x. G naught of x is just because x belongs to u and ug is in script a, therefore we define g naught of x equal to g of x. Are you following? Therefore, it looks like an upper bound, but there is something which you have to check. What I have to check? That u naught g naught is actually an element of script a. I want to say it's an upper bound. Yeah, I have to say it's an upper, sorry, it's in script u, right? This a is a totally ordered subset of this, and I want to say u naught g naught is an element of script u and it's an upper bound of a. So what is that I have to check? I have to check that u naught is a vector space of B and g naught from u naught to r is a linear map. See, I have to check these two things. Then only it will be legitimate upper bound for the totally ordered set A. You understand? Okay. These are all very easy, but if for the first time you are checking, okay, so start with any element x and y in u naught. Okay, what does that mean? That means x belong to some u1 g1, and it is that whenever I say it belong to, you understand what it means. X belong to u1, and similarly y belong to some u2 g2. Where are they? Both are elements in script A. What is script A? It's a totally ordered chain. Therefore, what do I know about u1 g1 u2 g2? One must be less than or equal to the other. Again, with a loss of generality, let me assume this is less than or equal to u2 g2, right? Therefore, my x, y both belong to u2, and u2 is a vector space. Therefore, x, y belong to u2, but u2 is a subset of u0. Therefore, x plus y belong to u0. Therefore, u0 is closed under addition. And similarly, if t is a scalar, then t times x belong to u1, which is contained in u0. I'm using this notation. Yeah. Therefore, it's a vector subspace. Next, I have to prove g0 from U naught to R is a linear map. Okay, please pause, review, proceed. That is again easy. We will keep the same notation. I want to prove G naught of x plus y, whether it is equal to G naught of x plus G naught of y. And similarly Tx. Let us look at that. Keep the same notation, then x, y both belong to U2. Okay, using the above notation, x belong to U1 G1, y belong to U2 G2, U1 G1 is less than or equal to U2 G2, therefore x and y both belong to U2. You understand? Therefore x plus y. Now x plus y, x, y both belong to U2, therefore x plus y belong to U2. Since x plus y belong to U2, G naught of x plus y, what is our definition? It is G2 of x plus y. But what is G2? G2 is a linear map from U2 to R. Therefore, G2 of x plus y is U2 of x plus U2 of y. But where is x? X is in U2, y is in U2. Therefore, G2 of x is same as G naught of x and G2 of y is same as G naught of y. Therefore, I have proved this. It's a linear. Yeah. And similarly, scalar multiplication, you can check it. Okay. Therefore, given a totally ordered subset of this, and I would have shown G naught, U naught belong to script U, and it's an upper bound for script A. All this work is only to conclude what? Zorn's lemma is applicable. Therefore, okay, Zorn's lemma is applicable. This is ordinary Z, not integers. Can be applied. Yeah. So let me note U H be maximal element. So there exists a maximal element of script U. You understood that? Now what does it mean? W is a subset of U and H restricted to W is F. And U is a vector subspace, H is a linear map from U to R. To conclude the proof, okay, enough to show my U is nothing other than V. Then I have an extension. Do you understand that? If I prove U equal to V, I got an extension. Right? This is VH, H restricted to W is F. You are through. Yeah? So I only have to show U equal to V. Okay? That is again easy. Okay? Suppose not. Let U be proper subset of V. Okay? So let V be in V, but not in U. Sorry, but not in U. Okay? Then let us look at, okay, U1 to be V plus R times V. Okay? I claim this is a vector subspace. Why? V1 plus S times V plus V2 times T times B. I hope our notation is clear. V1 is in V, V2 is in V, S and T are real numbers. This V is this. This I can rearrange as V1 plus V2 plus S plus T times B. Therefore, this is again an element of the form. Okay, it's an element of U1. You understand? And similarly, scalar multiple. Therefore, this is a vector subspace. You follow that? And my U, this is U. I write as V, sorry. This is U. U plus RV. Now notice that U is a proper subset of U1 because V belong to U1. I can take this to be 0 1 times P. 0 plus 1 times V. This is an element of U plus RV. Therefore, V belong to this, but V is not in U, right? Therefore, this strictly contain it. Okay, right. Now I define an extension. Now define G from U to R so that G of take any vector U plus S times V, define it to be HU plus S times G of V. I define it to be 0. That is, define G of V to be 0. Therefore, G of U plus SV define it to be H of U. You understand this? See what I want to do is I want to look at U1. So I want U1 G, okay, and I have UH. I want to say UH is less than or equal to U1 G, and this belongs to script U. If I show that, and then since okay, now this is a maximal element, right? And you say UH is less than or equal to U1 G1. That means those are equal. That means U must be equal to U1 and H must be equal to G because this is maximal. This should imply. But then that's a contradiction because U is not equal to U1. You understand? To arrive at this, I have to make sure that I have an extension. What should be G? G must be an extension of H. Have I done that? Yes, because start with any vector here. And why this works? Why this is correct? Because start with any element x in V plus R, sorry, U plus RV, then there is a unique way I can write it as U plus SV. Okay. Do you understand? If I write this as some U dash plus TV, then U must be U dash and S equal to T. Then only this is well defined. Okay. Are you following? It will be tough, but I hope since you are coming through this, you are already an MSc student who is in the 3rd semester. So I expect you to understand, pay attention. So I'm writing U1 as U plus R times V. What I want to claim is the direct sum. Okay, that's all I want to do. Okay, right? That means you give me an element X in U1, I can write it as a unique way, right? Why this is true? Because look at X minus X is 0, but that's equal to U plus SV minus U dash minus TV. That is U minus U dash plus S minus T into V. Okay, this is 0. That means T minus S times V must be equal to U minus U dash. But U minus U dash is where? This is in U. Okay. If T minus S is not equal to 0, if T minus S is not equal to 0, that means V equal to 1 by T minus S times U minus U dash. That is V belong to U, a contradiction. Okay, this is not possible. This is a contradiction. You understand? Therefore, T minus S must be 0. That is, T must be equal to S. Do you follow that? Therefore, T equal to S. Yeah. Therefore, when T equal to S, again look at that. That is U plus TV equal to U dash plus TV. Therefore, U again U minus U dash equal to 0. That is TV minus TV, which is 0. That means U minus U dash is 0. That is equal to U dash. You understand this? Therefore, I have shown this is well defined. Okay. And hence, I can define G of U plus SV because any element X in U has a unique expression U plus SV. Therefore, G of U plus SV I define to be H of U because it has to be linear, right? Therefore, it should be G of U plus G of SV. Therefore, H of U plus S times G of v. But are you following? Okay. You still have to show that H is linear. Uh, so is G linear? So how did you define? G of u plus SV is H of v. That's it. This is linear. Okay. Why? Because you start with any element x and y in u1, then x is u1 plus SV and y is u2 plus tv. Therefore x plus y, because of uniqueness, it is u1 plus u2 times s plus t times v. Therefore what is g of x plus y? This g of x plus y is h of u1 plus u2, but that is g of u1 plus g of u2, etc. Okay, but that in turn is g of u1 plus sp plus g of u2 plus tv. That is g of x plus g of y. I am going fast, but these are all very trivial BSc level mathematics, so you should feel comfortable. Therefore, this is G is linear. So now, okay, pause, review, proceed. So what I have done? Let UH is a maximal element in script U. I want to show U is actually V. Okay. If not, what did we prove? We had a U1 and a G, so that UH is less than or equal to U1G. Since U is maximal, I should get UH should be equal to U1G. That in particular will mean is U1. U must be equal to U1. This is a contradiction. Okay. Therefore, we conclude U must be equal to V. That means we got an extension. Okay. You can see how involved the proof is. Okay. But it's fun. Please go through that. This is the, because in functional analysis, I am sure no teacher has the patience, okay, to go through all these things. There is a lot of small things which you want us to check for the benefit of beginners. I have done that. I hope you understand. Yeah. So please go through this. In functional analysis, for this, as I said, this algebraic part of this. Actually, you will need an estimate. All our extensions should be continuous, etc., etc. But you can learn it there. Perhaps some other time I'll have a proof of Hahn-Banach theorem also. But don't worry, you just go through this, you will understand. Okay. And for more details, look at our book on functional analysis. I hope you enjoyed. This lecture would have been slightly more demanding, but for okay, if you have learned in algebra well, it should not be difficult. Because most often what I was checking, something is well defined, something is a vector space, something is linear, right? These are all very easy, right? Okay, I hope you enjoyed. Okay, please pass on your comments whether you liked it or not, whether you understood. Okay, thank you very much.